This podcast is brought to you by LMU Munich.
In the first session, the main highlights that we discussed were the fact that in two-dimensional field theories, there is the ubiquitous central charge. There is the ubiquitous central charge, which appears, for example, in the trace anomaly equation. That's one thing that we discussed. Then we discussed that the energy momentum tensor transforms inhomogeneously by some term that is called the Schwarzian derivative. That's another thing that we discussed. Then we studied the entanglement entropy, or more generally the Rayleigh entropies, for an interval, AB. And we have argued that we've argued that is given by a minus b to the power n minus 1 over n with the c over 6. So we argued for such a formula based on conformal invariance, and you see that it's again determined by the central charge. And also I've mentioned that if you take a more complicated set than just a single interval, then it cannot be in general uniformized to the sphere, and the Rayleigh entropies would be far more complicated. And even in minimal models, they are not known. Even though it's a well-defined exercise in conformal field theory, it hasn't been yet solved. And then from that, we also derived the von Neumann entropy for a single interval. That was given by C log A minus B. And finally, we discussed that these are all results about conformal field theories in 2 dimensions. And then we have briefly discussed RG flows between 2-dimensional conformal field theories, which can of course be realized experimentally or in Monte Carlo simulations very easily. Experimentally, this would be realized by various spin chains, and you can prove a non-perturbative inequality, which I have not proved, but in the second session today, I will give you an argument that is different from the original one, which establishes that. Some simple argument of why this is non-perturbative, a non-perturbative property of all 2-dimensional renormalization group flows that are unitary. Okay, so this was the set of results that we've covered for 2-dimensional field theories. Oh, and I forgot to mention that by deriving all of this, there was a simple corollary, which is that every scale invariant field theory is actually conformal invariant and therefore invariant under the Virasoro group. Okay, so there was this additional spin-off of this discussion. Okay, now in the second session, we discussed the three-dimensional field theories. So 3D CFTs and 3D theories. Okay, 3D theories. And the first novelty was that free QED in 3 dimensions is scale invariant but not non-conformal. That was the first novelty, and this theory is actually quite subtle. We argued for the fact that it's actually described by a normalization group flow from some scalar which has 0 radius to some scalar that has infinite radius, i.e. a normal scalar. So that was a subtle theory. And then we discussed the S3 partition function, or that's more common, its log, and we discussed the fact that it has a cubic divergence, where A is the radius of the 3 sphere, a linear divergence, and some coefficient f. So actually there is a minus here conventionally. Coefficient f, which is, we argued, physical. So we argued that f is physical, cannot be removed by modifying the cutoff, and finite in many interesting 3-dimensional conformal field theories. Okay, so f is physical and finite and so on. And then I quoted the fact that one would like to see whether in 3-dimensional quantum field theories there is this inequality between the f of the UV and f of the infrared. And we studied one example to this effect, in which you could verify that this is indeed true. And it has been studied very extensively in many, many examples, and in all of them it seems true. Okay, so the first thing that I would like to, so today I would like to start by discussing two things. So the first question that I would like to discuss is the physical interpretation of f. Okay, it's nice that it's some S3 partition function, but how are you going to explain to an experimentalist how to measure it? Okay, I mean, so it's how can one, in principle, for example, measure it, say, for boiling water? And now that I've said boiling water, let me just emphasize that by that I mean water has a second order phase transition point, which is described by a 3D Ising model, which is a conformal field theory. And its critical exponents describe the critical exponents of the second order phase transition point in boiling water. The second order phase transition occurs at maybe 100 atmospheres and 300 Celsius. So how are you going to, suppose you wanted to measure f for this model, so how could you in principle think about it? So what's the physical interpretation of f? That's the first question. And the second question would be, how can we try to, well, would be some attempt, a very incomplete attempt, I don't know how to complete that, but a very incomplete attempt to try to prove this inequality using normal quantum field theory tools without alluding to some other assumptions that I will mention. So this attempt will be quite feeble. In fact, I'll just be able to prove that f is positive in a very limited set of theories. So, but that's what I can do. Just using normal quantum field theory tools, but there are other approaches which seem much more successful. Okay, so this is the plan for now, and then there will be a bit of, I'll mention a bit of supersymmetry on S3, which allows to compute f exactly, non-perturbative. It gives us lots of like data about f in supersymmetric field theories. Okay, so these are some things that I would like to cover now, and then we'll go on to 4 dimensions. Okay, let's start from the physical interpretation. So f is basically given by the logarithm. This is going to be somehow not very detailed. I'm just going to draw pictures and to try to explain what f measures. So f is given by the partition function on the sphere, a log of this partition function, okay, on the sphere. So I'm just denoting this by that, minus log of the partition function on the sphere. And this is a very abstract object to study. First of all, in fact, it's divergent, as we've discussed. So there is a cubic divergence, and there is a linear divergence, and you need to very carefully subtract them to find f. And we've discussed that you need to make sure that your regularization scheme maintains diffeomorphism invariance. Otherwise, you may subtract lambda slightly incorrectly, and then you would contaminate f by order 1. So if you were to study this theory on the lattice, for example, it would be not extremely trivial to measure f, even on the lattice. Suppose you take an S3 and you tessellate it in some way, and you put it on the lattice. And let's for now ignore the issue that the point group is bounded. But suppose you do it on the lattice, and then, I mean, there would be some divergences, and you subtract them. How would you know exactly what's the finite piece that remains? You would need to, so in principle, you would need to start studying many correlation functions, and you would need to make sure that your regularization scheme is consistent with the word identities of diff invariance for these correlation functions. And after you've made sure that you know what you're doing and your regularization scheme is diff invariant, you could perhaps measure f. It's extremely challenging, but not impossible, and it was done for free field theories on the lattice. But physically, it's still not clear what this kind of observable means, especially that, I mean, we have a good physical intuition for spaces of the following sort. So if I told you that f is the partition function of some 2-dimensional space times r or S1, doesn't matter, there would be some reasonable physical intuition behind this object, because you could think about it in canonical quantization, that you are just counting states in the Hilbert space of the theory on sigma. But given that S3 is not a product of some two-dimensional space and a circle, the Hilbert space interpretation is lacking. So it's not clear what F is counting. I mean, from this, the fact that this inequality is suggested to be true, you could say, okay, this is somehow counting degrees of freedom, but it's not clear which degrees of freedom and why. Okay, so let me try to explain some other interpretation of F that maybe is more intuitive. Okay, so suppose you start from a completely different object. So forget about that. We'll start now from a completely different object, which is just field theory in R3. It's three-dimensional field theory in R3. So at 0 time, when the time is just 0, we have some two-dimensional space. Okay, and in this space, we can try to study the entanglement entropy on various regions. So in particular, one nice entanglement entropy to study is to take a half space. So A in the notation of the previous sessions is just a half of space, a half of R2. And this is 0. You can say that this is X and Y and this is 0. Okay, so it will be nice and symmetric. Okay, so one can try to study the density matrix of A to integrate out a half space. And then one can also study the Rayleigh entropies of A. Now I understand that it was explained to you that the density matrix of a half a space is known. And there is some, well, it was discovered many, many years ago by axiomatic quantum field theorists. And then it was physically, I think it was, there is a simple explanation of why this result is true in the work of Kabat and Strassler, for example. But, so this is a non-perturbative result that I'm just quoting, I'm not going to prove. There's a very simple argument in Kabat and Strassler that you can find, or in the previous axiomatic work. So the density matrix of a half a space is exactly known, even for non-CFTs, and it's always given by exponent of minus the boost operator. So K is the boost operator. So it's the boost operator which leaves that intact. It's like rotations in the direction, time, and that. So this is the boost so K is the boost operator. So this is a special case. The half a space is a special case in which we can express the density matrix in terms of an exponent of an integrated charge. So this is a particularly simple density matrix, which is of course very similar to a thermal density matrix, where the thermal density matrix we have e to the minus h, and here we have e to the minus k, where k is the boost operator. So this is a particularly simple density matrix, and it's only true for half a space. For more complicated spaces, one does not believe that the density matrix can be written as an exponent of a conserved charge or some sufficiently nice operator. It's believed to be non-local and much more ugly. But for a half a space, this is supposed to be true. Okay, so the next step so we can try to draw some diagram. So let's just ignore one of the dimensions of space so that I can draw a Rindler space. So this is time and this is x, and this is the Rindler wedge. So this is x, this is t, and this is x equals 0, and this is the Rindler wedge. Okay. So what we're doing is we're measuring the entanglement entropy over this half a space, where in this picture, in this diagram, I have omitted one of the directions of space. So the boost generator is, of course, acting like that, right? So the boost generator, the Killing vectors of the boost generator look like that, and the exponent of this guy gives you the density matrix of a half a space. Now there is a conformal transformation, So this would be just relevant for CFTs. This is always true, that the density matrix is e to the minus k. This is always true. But now I'm going to use a conformal transformation. So the identification of this observable with the observable that we'll get now is only correct for CFTs. But there is a conformal transformation that takes this wedge with this conformal killing vectors, this killing vectors, and transforms it to a circle. So this is time is now going out of the blackboard. Well, let me try. Okay, I'll try to draw some three-dimensional picture. So there will be a circle at time equals 0. And then there's the causal complement of the circle, which looks like this. So there's some diamond. So there is some diamond of all the points that depend causally just on what is inside the circle. And in this diamond, there are some vectors, some conformal killing vectors of some sort, like this. Let me just draw a less cluttered picture. So the idea is that there is some circle, and so the half space which sits at time equals 0 is mapped to a circle, and the killing vectors which describe what's called the modular Hamiltonian, which is the density matrix, the exponent of the thing that defines the density matrix. These lines transform to some lines in the causal wedge of the circle. So they would look like this. Okay, so what I'm saying is that there is a conformal transformation that takes this Rindler wedge and transforms it to the causal evolution of some circle. And these lines look like this. These vectors look like this. So this means this is nothing more and nothing less than the entanglement entropy of a circle. So that means that the entanglement entropy, or the Rayleigh entropies, it doesn't matter. So all the Rayleigh entropies of a half space in three-dimensional field theories, so this is the identity that we get, are actually equal. So they're actually equal to the Rayleigh entropies of a disk. And it doesn't matter what's the radius of the disk, because this is a conformal field theory. So, and there are no anomalies in three dimensions, so all the disks are the same. Okay, so there is a conformal transformation between a half space and a disk, and the modular Hamiltonian can be found too by just taking the boost generators and acting with these conformal transformations on them. So this is an interesting result that relates the disk and a half space for conformal field theories. Actually, you should not be surprised by that, because we've seen previously the one-dimensional version of that. So when we proved yesterday, when we argued yesterday that the entanglement entropy of an interval is the same as that of a half space, I mean the semi-infinite line, that's just a special case of that. The disk is analogous to an interval, and the half space is just a semi-infinite line. So exactly that was shown last time. Okay, now the final thing, this is the less trivial thing to understand, but there is another useful map. So this object, which is the, yes?
When you have been talking there about a half space, you mean a half space in the xy plane?
Yes.
But there you mean the wedge in the px plane?
Yeah, my drawing capabilities are very limited. What I'm trying to say is the following. When you define the entanglement entropy, you choose t equals 0, and you choose some subset of R2. Okay, so here you choose the half space as a subset, and here you choose the disk as a subset.
There you also mean with half R2 the xy plane? Or?
Yes, it's always. Yeah, I can, if I could, I don't know how to, I couldn't have drawn another direction here, but I should have. So what I'm trying to say is that there are two things. One is that the disk can be mapped to a half space. That's just a statement about conformal transformations of R3, which act on t equals 0 in this way. So there is some conformal transformation of R3 that takes the 0 time slice to itself, and the half space is mapped to a disk. So the entanglement entropy of a half space at t equals 0 is the same as that of a disk at t equals 0. But you can do a little bit more, because we also know the modular Hamiltonian for a half a space. The modular Hamiltonian is this k. The density matrix is given by e to the minus k. So we know that the density matrix is given by boost generators. So you can take the same conformal transformation in R3 and see what is the resulting density matrix of the disk. So I'm trying to say that this is true, and we also know the density matrix of a disk. Okay. Okay, now the last thing that one can show is that this can be conformally mapped. So this object can be conformally mapped. This is the disk entanglement entropy. So this object can be conformally mapped to two interesting observables, two other interesting objects. One is the S3 partition function. So that's exactly our hero. You can show that this can be just you can almost see that this looks like an S3 if you just rounded the corners. But you can actually make it completely precise. You can find a map that takes this object to S3 and sends everything else to infinity. So the edges the boundaries would be sent to infinity, and this would just look like S3. So you can almost see that from the picture. So this by itself can be mapped to S3. And it can also be mapped to another interesting object, which is a hyperbolic two-dimensional space times S1, where the radius of the S1 is 2 pi, in units where the radius of the hyperbolic space is 1. Okay, so there are two interesting this can be mapped conformally to two interesting objects. So we see that there is a sequence of, if you want, dualities or relations for conformal filters, which is that the S3 partition function, which is the object from which we started, is the same as the disk entanglement entropy. This is the von Neumann. So here, this mapping is true, and it relates the von Neumann entanglement entropy of the disk with the S3 partition function. We don't the Rayleigh entropy is mapped to something much more complicated, like ends covering of the sphere. So the Rayleigh entropies would map to some ends covering of S3 and to slightly other spaces. But if you just want the von Neumann entropy, then this is literally true. So this is for the von Neumann. This is when this is the von Neumann entropy. If you want the Rayleigh entropies, then you map to slightly more complicated spaces with various conical singularities. But just for the von Neumann entropy, this is literally true. So the S3 partition function is the same as the von Neumann entropy of a disk. So that's already a nice interpretation. The object which we started from that didn't have a manifest physical interpretation can now be understood as some kind of entropy of a pretty standard type of some disk. And it can also be mapped to the thermodynamic entropy. So this is like the quantum information entropy. But then it can also be mapped to the thermodynamic entropy of the theory when you study it on hyperbolic space times R. So there is some thermodynamic entropy that you can compute by computing the partition function on H2 times S1 and taking a derivative with respect to temperature, as you would usually compute the entropy. So there is the sequence of inequality, sequence of relations. So this is minus log, to be precise. Minus log of z, which is f. Okay. So f is given by the von Neumann entanglement entropy of the disk, which is also the same as the thermodynamic entropy of the theory in hyperbolic space. So in principle, this is a compelling interpretation of what f means. It's some quantum information theoretic entropy. And also this is nice. This shows that the thermodynamic entropy on hyperbolic space is monotonically decreasing, which is an interesting feature. Just as a curiosity, there was a lot of work in the end of the 90s on an attempt to show that the thermodynamic entropy of R2 times R is monotonically decreasing. So this is like the ordinary free energy density particles. And there were people thought that maybe just the ordinary thermodynamic entropy is monotonically decreasing, but this is false. People found the counterexamples. People found RG flows in which this does not decrease. But the thermodynamic entropy on hyperbolic space needs to decrease by this sequence of relations. So that solves like very long-standing problems in the theory of quantum filter in 3 dimensions, where now there's a sensible candidate that seems to always decrease, and it's interesting because here hyperbolic space appears, while previously people tried with R2 and they failed in the end of the 90s, and it's also related to the quantum information theoretic entanglement entropy of a disk. Yes.
How do you show that, like, what is the way to show that essence, that it's like, because like the partition function, it's not only geometric, like the partition that looks like a sphere, because you were talking about the partition function on the sphere.
Say again. So this is the partition function of the sphere,
Yeah.
ZS3. So what is the question?
You said that this is equivalent to, so how do you see it?
How do you see that, for example, this is equivalent to this?
Yeah, not just, okay, you said it looks like a circle, that's,
No, I'm just saying that there is a conformal transformation that takes this object to S3. So let us be slightly more precise. The Rayleigh entrophies are computed by taking the ends covering of this space, as we've explained. You need to take some branch covering of the disk, of R3 with some singularities on the disk. So if you wanted to compute the Rayleigh entrophies, you would have to study the partition function of some complicated branch covering space. And then this can be mapped to some branch covering of the sphere. Okay? Now you can take n going to 1. So at this point, so far it's still completely rigorous. Okay? So the partition function of some n branch covering of the disk of R3 with the disk singularity can be mapped to some nth branch covering of S3. So these partition functions agree. And then you can take carefully n going to 1. So on the left-hand side, you get the von Neumann entropy, and on the right-hand side, the branch covering disappears formally. So you get just ordinary S3. Okay, so you see that the thermodynamic entropy on hyperbolic space needs to be monotonically decreasing, and it's the same as the von Neumann entropy, and it's the same as F. All these equalities are only true at CFTs, but since the inequality is about the endpoints of RG flows, then we understand that these quantities are monotonically decreasing. Okay, are there any further questions about that? All the references can be found in the notes. So there are many people who are involved, of course, and I'm not citing almost anybody. Yeah. What? No? Okay. Okay. So this is some hopefully appealing interpretation for what F is counting. So this is some, it can be interpreted as thermodynamic entropy or quantum information theoretic entropy in 2 different situations. Okay, now let me say that using inequalities that are supposed to be satisfied by the entanglement entropy, it has been proven or argued that this is true. So there is a formal proof of this by Cassini and Huerta. Their proof utilizes especially this point of view. So they study this object, and they use this subadditivity inequality, which we already mentioned, and they turn the crank, and it's quite a non-trivial construction, and they can arrive at this inequality. Of course, their proof assumes that the von Neumann entropy can be defined for very complicated spaces, and which is non-trivial because even in 2 dimensions, in very simple examples, it's not clear that this can be done. But if you assume that the von Neumann entropy can be always defined, and it's indeed a correct observable in the continuum, then you can at least formally manipulate the subadditivity inequality and arrive at this inequality. A conventional field theoretic proof is still lacking, where one would not have to deal with this von Neumann entropy, but some attempts are being made. Okay, now let me discuss the von Neumann entropy of the disk in a little bit more detail. There is some extremely interesting feature that I would like to emphasize. I just want to study this object in CFTs a little bit more. So we have a disk, and we're studying the vacuum entanglement entropy, where we integrate everything that's outside of the disk away, and one remains with this density matrix. So one thing that that you could have asked about is that this partition function is divergent. And to arrive at this finite parity f, you need to throw away some cubically and linearly divergent pieces. Similarly, the von Neumann entropy is divergent. So when we write these equalities, they have to be understood in terms of the physical data. So there is some underlying physical data that you cannot remove by throwing away various power divergent terms, and they have to agree. But the power divergences are more subtle. So I just want to discuss a little bit the question of why the von Neumann entropy of a disk is even physical. So if you compute it in simple examples, you find that there is a linear divergence. Let's call the radius of the disk A. Okay, so what? If you compute it in simple examples, you see that there is a linear divergence plus, let's call it f. Okay, since we know that this is supposed to be the same as f. And one can again ask the question of why is this physical? Why is f physical? You could have changed the cutoff lambda by a tiny bit, 1 over a, and you could have removed f. So you could have asked this question again. Now let me say that the von Neumann entropy is divergent because you integrate out modes that are outside of the disk and you retain modes that are inside the disk. But some modes are extremely close by. Like for example, there are the modes that are near the boundary, which are extremely strongly entangled, and you want to artificially remove those while retaining the ones that are inside. That causes divergences. And this also explains why these divergences are proportional to the linear dimension of the boundary A, because you're essentially getting rid of all these pairs of strongly entangled modes that are spread more or less uniformly over the boundary. Now, more precisely, the theoretical setting is that one is allowed to write counter terms on the boundary of the entanglement entropy region. So that's supposed to be, so the general story is supposed to be the following. So suppose you want to study the von Neumann entropy for some general region A. And you would encounter divergences. So what are the rules of the game? How do you know what's physical, what's not physical? So in principle, the following is supposed to be true. One is supposed to write local diff invariant, everything that you would like. Local diff invariant counter terms on the boundary of A. What's the physical intuition behind it? The physical intuition is that these entanglement entropies are divergent because you are integrating modes which are very close by. So the counter terms should be localized on the boundary because this is where the thickness comes from. So this is the idea. So this is like the renormalization. This is like the rules for renormalizing entanglement entropies, that we remove or add counter terms on the boundary. So let us try to do that for the entanglement entropy. So first of all, you can write the following counter term on the boundary. So in this case, the boundary is just S1, and we can just write dx, where x is a coordinate on the boundary. So x is just a coordinate on the boundary, and this is like a cosmological constant term on the theory of on the boundary of the entanglement entropy. So this is one good counter term, and we put a UV cutoff here, lambda. And that exactly reproduces this divergence because the length of the S1 is A, up to some 2 pi's. So we see that this linear divergence can be explained by a cosmological constant on the boundary of the entangling surface. So that's a legit counter term. Now there is a certain confusion. You could have added the following counter term, K dx, where K is the extrinsic curvature. So this dA is of course embedded. dA is embedded in R2 or R3, and you are allowed to write anything that's local and diff invariant. In particular, you are allowed to use the metric, the extrinsic curvature, and so on. So K is the extrinsic curvature. Okay, now this seems to be very confusing because this does not scale with A linearly, because as you know, this is actually somehow amusing that we're sitting in the Kara-Teodori Hall-Zane, and we're discussing this thing. It's of course very closely related to what he did. But anyway, K is just the extrinsic curvature, and this is just 1 over A for a circle that is embedded in flat space. So this would seem not to scale with A, it's dimensionless, and it would seem to render the finite piece F ambiguous. Okay? So you would say that F is unphysical, and these equalities don't make any sense because there is a counter term for F. So as an exercise that I will not tell you the solution of now, you can try to think why this is not allowed. There is some particular reason for which this is not allowed, and it's not trivial. There is some symmetry of the problem that this breaks. I will not, but this is an exercise that I'm leaving for you. In essence, there is an argument that removes this counter term, that disallows this counter term. And so F is physical because this counter term doesn't exist. But you should try to think about that. If anybody has any idea, then you can try to tell me now. Okay. So it's not entirely obvious. Okay. So the conclusion is that F is physical because this counter term cannot exist for some reason. And this was a general comment that I wanted to make about disentanglement entropy. Fine. Now let me just quickly discuss another question, which is, okay, suppose there is this argument by Cassini-Huerta, which is extremely beautiful, where they manipulate entanglement entropies. But of course, they study the entanglement entropy of not just the circle, they construct something very complicated. And suppose you don't want to discuss the entanglement entropy and you just want a proof. Suppose you just want to understand why this might be true from, let's say, conventional QFT. Conventional QFT tools. It's a statement about conventional QFT, so one may hope that it can be proved without alluding to the existence of the von Neumann entropy, because we don't have a non-perturbative definition of the von Neumann entropy. We don't have a path integral definition of the von Neumann entropy. We only know how to define it as the limit of the Rayleigh entropies, but this limit may or may not exist. So one would like to use ordinary quantum field theory tools in which there is a path, for which we have at least a formal path integral definition. So this is an inequality about the path integral, so one should hope that it can be solved. So I don't know how to do that, but I would like to present an argument which is extremely weak, but maybe it's in the right direction. So I would like to prove that F is non-zero for unitary theories, is bigger than 0 for unitary topological theories. So you see that this is very far from any interesting statement of any sort, but it might be in the right direction, and this is the best one can do at the moment. So as we've discussed last time, F is non-trivial even when you have topological matter. So F counts topological matter, and you would like to at least understand why F is positive for topological matter. Let me just remind you that for the pure Chern-Simons theory, it was a half log K, so it was definitely positive, because the level of the Chern-Simons term needs to be bigger or equal to than 1. It's quantized. So it's slightly non-trivial. If you allow the half integer Chern-Simons term, then this would not be positive. But it's only consistent when K is bigger or equal to 1, so this is non-negative. This is non-negative, okay? So, and also, of course, Ed Witten famously computed F for SUN. This is for U1K. But of course, Ed Witten in his famous paper on Jones polynomials computed F for SUN gauge theories, topological gauge theories at level K. And he found a certain answer that is also always positive. Let me just quote the answer. So, well, he found that something that looks like n over 2 log of k plus n. This is for for un level k. This is Ed Witten's answer for un level k. It's exact. And then there's some sum over things that look like n minus j, and then some log of sine of something. The formula is in the notes. Sine of j over something, k plus n. The full formula is in the notes, but you can check it's always positive. So, and there are many topological field theories in 3 dimensions And at least it would be nice to have an argument of why f is always positive. So let me get to the argument. Of course, it would be extremely nice to at least prove that for propagating matter, unitary matter, the number of degrees of freedom is positive. Of course, I mean, the motivation for proving that f is positive is that it should count the degrees of freedom. So one expects that it's always positive. Let me also mention a historically interesting fact, which is that in 4 dimensions there is a certain candidate for RG flows that is called A, which we'll discuss a little bit in the next lecture. And this inequality was proposed many, many years ago, but it was only proven that A is actually positive in the 2000s by Hoffman and Maldacena, in 2009 or something, or 2008. So it took a lot of time for even that to be established in 4 dimensions. So in 3 dimensions there is not yet an argument. Only for topological filters, I'll give you an argument now. Okay, so here's the argument. So the argument is the following. This is just for topological matter. Remember that. So let's start from S2 times S1. For topological filters, there is an interesting fact that the partition function on S2 times S1 is 1. That's our starting point. The reason for that is that S2 times R is what's called radial quantization. It's a conformally equivalent. So this is the 3-dimensional cylinder. S2 times R is a 3-dimensional cylinder. It's conformally equivalent to R3. And the partition function on the partition function on S2 times S1, when the S1 has radius beta, does nothing more than counting local operators in R3. So it counts local operators in R3 with this weight, E minus delta beta, where delta is the conformal dimension of the operator. So it's just the partition function of local operators by this conformal equivalence. Now, in topological filters, there are no local operators other than the unit operator. So this is 1 for any S1, for any radius of the S1. Good. Now, this is some kind of cylinder. So the picture is that S2 times S1 is some kind of cylinder. Okay, the next step, are there any questions about this step? That S2 times S1 counts local operators and therefore it's trivial for topological filters? Okay, so the next step is that this is some cylinder. Okay, S2 times S1 is just some cylinder. And since the theory is topological, it doesn't depend on the metric that we put on S2 times S1. So we can make the S2 like this. So we can make it very, very squishy, like a big, big sausage. Now, like a Wurst. Okay? So we have this very big sausage, and the partition function is 1. But now this can be interpreted in a completely different language as the propagation of some state, because when we have a very, very long, we can now think, so time usually runs on the S1. Time in this picture runs on the S1. You see that this is like a partition function with Euclidean time being on the S1. But now we can interpret it in a dual channel where time runs here. So one can interpret the partition function on S2 times S1 as the overlap of some state with itself. So there is some thingy here that creates some state which propagates, and it meets the same state that comes from the other side. So because you can take this time to be very, very long, this is just the vacuum state that is created by the tip of the sausage. So psi is like the state that is created by the tip of the sausage. More precisely, if you think about time as running in this direction, then the theory now lives on S1 times S1. So we now interpret the theory as if it's living on S1 times S1 times R. So this is our time. And we can think about the theory as if the space is a torus. And the torus shrinks. Yeah, so in the end the torus shrinks a little bit, but it's a state in the Hilbert space of the torus times R. And its norm is 1 by the previous assertion that the partition function is 1. So, so what I'm trying, okay, is this clear or not? So is it clear where the torus came from, for instance, or no? Okay, so one component of the torus is what used to be the Euclidean time, and the other component of the torus is just from the S2. So the Euclidean time never shrinks. So this is what used to be the Euclidean time. And the other one eventually shrinks. So this is the tip. But away from the tip, it can be psi can be interpreted in the state as a state in the Hilbert space of T2. Okay, fine. So if there are any questions, I can try to explain it in a different way. Yes?
Can one think of psi as created by some fusion operator out of the vacuum?
Yes.
What kind of fusion operator?
It's some operator on T2.
What operator?
What operator? I don't know. But well, there is some, because this is very long, and this the cross section. So if you just take a constant t, the cross section is a torus. So this is some state in the Hilbert space of the torus. I don't know what precise operator would create it, but I think it can be answered. Okay. Fine. Now the next step is that we can do the following nasty trick. S3 can be viewed as follows. So S3 can be viewed in various ways. One is the hop vibration. So it can be viewed as an S1 that sits on top of an S2. But there is a slightly more useful way for us. So S3 can be viewed as a torus that is fibered over an interval. And we can take the interval to be however long you want it to be. Because it's topological, and then we can increase the interval indefinitely. So S3 can be viewed in the following way. So everywhere along the torus there are two cycles, S1 times S2, S1 times S1. So let's call these two cycles A and B. So S3 can be viewed as a torus that sits on a line. So it's locally T2 times times the real line. But here A shrinks, and here B shrinks. Okay, so you can think about this as a sphere as if you have a torus in which, like in one end of the interval, the cycle A shrinks, and the other end the cycle B shrinks. And indeed, there is a metric. There is a metric for S3, a metric that looks more or less as follows. Maybe I'm getting it. It's in the notes. So even if I'm getting it slightly wrong, it's fine. So there is sine squared theta, and then there will be deep psi squared. And then there will be, so let's say the theta runs from 0 to pi over 2. So then there will be cosine squared of theta d phi squared. So one can actually write down a metric for S3 of this type. So you see that there is a torus consisting of the angles psi and phi. And as a function of the interval theta, psi shrinks at theta equals 0, and phi shrinks at theta equals pi over 2. So one can actually write a metric on the round sphere of this type. Okay, now, so this means that so here one of the cycles of the torus shrinks, so we create exactly the same state psi as in this picture. It's exactly the same. It looks exactly the same as S2 times S1, only that here A shrinks and here A shrinks. So the difference is that here A shrinks and here A shrinks. But in S3, A shrinks on one side and B shrinks on the other side. So the difference between the cylinder and the 3 sphere is that on the cylinder, in both directions, A shrinks. Sorry, the difference between S2 times S1 and S3 is that on S2 times S1, on both sides of the interval, the same cycle shrinks, and in S3, a different cycle shrinks on the two ends of the interval. So this is just the topological difference between S2 times S1 and S3, that the same cycle or different cycles shrink. So therefore, this means that the S3 partition function is given, so what comes in at minus infinite time is exactly the same state. And what comes out at plus infinite time is also exactly the same state. But only in the middle, we need to twist the torus. So we need to change what we call A and B. this is like a fiber bundle, right? A non-trivial gluing of, so that you can think about it as a fiber bundle where the base is an interval, the fiber is a torus, and in one case we need the non-trivial transition function that would make an S transformation, and in another case we don't need such a thing. So the S3 partition function can be interpreted in this way, where S is an operator that acts on the Hilbert space of the torus, which implements the S transformation. Now the key property is that this thing scores to 1. So if you make this transformation twice, you go from A to B, B goes to A, you're back to yourself. So this now is just a stupid inequality in linear algebra. This is smaller than this. So if you sandwich an operator whose norm is 1 in between some states, then this matrix element has to be smaller than the norm, which is 1, and therefore F, which is minus log of Z3, is bigger than 0. And that's it. Okay, so this is an argument that shows that at least for topological matter, F is positive. Are there any questions about the argument? Yes?
Originally you said when you were going to give an argument, it was going to be very strong. It was not the best argument. What about this is not very strong?
No, I mean, it establishes what it means to establish, but it's just physically not the best, not what you could hope for. This just shows that F is positive for topological matter. I mean, but the F theorem should be true for any unitary theory with propagating degrees of freedom, and in particular, F should be positive for theories with propagate. I don't know how to prove that F is positive once you have propagating degrees of freedom. You can ask what in this argument goes out of the window when you give up on the assumption that everything is topological. And essentially everything goes out of the window, because you cannot make the S2 times S1 look like a very long sausage. If there is non-topological matter, it would be sensitive to the metric. So this goes wrong. This is not true because there are local operators. Like essentially every step goes wrong. Every step is not true. So this is probably very far from the most interesting physical question, but it establishes something. That S3 partition functions of topological field theories give a positive F. Okay, are there any questions? Any other questions? Okay, finally, I would like to make some brief comments about the supersymmetry. They will not be as detailed as this. So one of the themes of the literature in high energy physics recently has been exact computations of partition functions on curved spaces. And the statement is that we can compute the partition function of S on S3 for every n equals 2 field theory, n equals 2 in 3D. So we can do that non-perturbatively. There is a matrix model. Okay, and that gives you, of course, lots of data for F. In particular, for topological field theories, you can compute it. For some topological field theories, you can compute it in this way. Okay, so I just wanted to just make very brief comments about the requirements you need to satisfy to be able to do that. And I will not go into much detail. So just a few very general comments. So n equals 2 on R3 is just a force. So this is just this supersymmetry in 3 dimensions with 4 supercharges is very similar to n equals 1 in 4 dimensions, which you may know well. So this has 4 supercharges, and the algebra that it satisfies is something of this sort. So it's P, and there may be also some central term. There may be some central term in the algebra, depending on what you're doing. So the algebra is more or less what you're used to from n equals 1 in 4 dimensions, and this is what, and much is known about these theories in flat space. Now, on S3, on a 3 sphere, the situation is a little bit different. So to put, I'm just giving a very, very rough introduction to what what can be done on S3. So in flat space, everything is very simple and mirrors very closely the situation in 4 dimensions. Now, to put the theory on S3 and preserve supersymmetry, you need to work a little bit harder. In fact, the prejudice could have been that you couldn't put a supersymmetric filter on a sphere sphere because a sphere sphere is the same as the Sitter space, and it's hard to preserve supersymmetry in the Sitter space, which is a well-known fact. Yet it's possible to put supersymmetry filters in a sphere sphere, but one has to work a little bit harder. So to put the theory and preserve SUSY on S3, you need an additional ingredient which you do not need in flat space, and that is an R symmetry. So let's call the R charge R. So only theories which have an R symmetry in flat space can be studied on the curved manifold S3. And the supercharges transform in the following way. So in flat space, the supercharges are just spinors of the Lorentz group. On the sphere sphere, the situation is a little bit different. The isometry group of the sphere sphere is just SO4, which is SU2 times SU2. So when you discuss supersymmetry on the sphere sphere, you have to say, how do the supercharges transform under SU2 times SU2? That is analogous to saying that the isometry group of the 3-dimensional flat space is just SO1, 2, SO2, 1, sorry, and the supercharges transform as spinors of that. So the supercharges, so it turns out that you can preserve 4 supercharges. So for theories with an R symmetry, so this is all for theories with an R symmetry, otherwise it's impossible to preserve supersymmetry. So if you have an R symmetry, it turns out that you can preserve 4 supercharges out of the 4, out of the original 4 in some sense, on S3. And they sit as 2 doublets under, let's call this SU2 left and SU2 right. So we have 2 doublets of SU2 left, and they're all singlets of SU2R. So we have 2 doublets of SU2 left, and they are neutral under SU2 right. So that's the superalgebra. And the superalgebra, roughly speaking, looks like as follows. So one has some isometries. So when you multiply 2 supercharges, you generate some isometries of S3. That's the analog of P in flat space. But one also has an R. So one also generates an R transformation in general. So an R symmetry is necessary for this construction. Okay, now what people do in localization is that they start from the filter in S3, which you construct by following this prescription, more or less. And then they deform the theory by Q, V with some parameter. And then there is some argument that it's independent of this parameter because it's Q exact. So when you differentiate with respect to this parameter, you get Q of something, which doesn't change the correlation functions because it's Q exact. And you then hope that you can choose V judiciously such that when t goes to infinity, this is some positive definite term, and it dominates over the original Lagrangian. So if you can solve this simpler field theory, you can compute the partition function for the original theory. But I'm not going to go into details. All I wanted to say is that one can preserve supersymmetry on S3 under the condition that there is an R symmetry. And there is lots of literature on how to compute partition functions. And you can look at that literature if you're interested in, for example, studying how f changes as a function of the RG flow, as depending on the RG flow, and so on and so forth. Or you want to check dualities. So this is a very useful development. Okay, so I would like now to start discussing 4-dimensional field theories, unless there are any questions about 3. Any more questions about F or von Neumann entropies or any of that? Okay, so let me know. Okay, on the blackboard. Can you ask again? Can you ask again?
What are the interesting features of the von Neumann entropy and the S3 then? If it's supersymmetric?
Yeah. So okay. So that's a good. So the partition function S3 is in CFTs is identical to the von Neumann entropy on the disk. Okay. So for supersymmetric filters, n equals to supersymmetric filters, we have, in some sense, lots of data. We have lots of data about the von Neumann entropy on disks of such theories, because the S3 partition function is the same as the von Neumann entropy on the disk. Now, there is an interesting question of what about Rayleigh entropies? That's an open question. There are many. These are many open questions already. I already mentioned many open questions, but this is an additional open question. So we know the von Neumann entropies of a disk in interacting supersymmetric filters, because we can get them through the S3 partition function, which can be localized. But suppose you want to know the Rayleigh entropies of the disk. So you would need to study some nth branch covering of S3, and you would need to try to localize that, the partition function of some branch covering of the S3. Now, it turns out that the branch covering that you get by following your nose is not supersymmetric. So the chances of localizing it look very dim. But you can modify a little bit the observable that you're studying by changing essentially so there are these conical singularities that you would get. And you can put some gauge fields around these conical singularities so as to preserve supersymmetry in the nth branch covering. And then you can compute the partition function. It doesn't quite compute the Rayleigh entropies, but you can call this object supersymmetric Rayleigh entropies. So it's slightly different from the ordinary quantum information theoretic Rayleigh entropies, but it can be done nevertheless. So you can study some nth branch covering of S3, and you can preserve supersymmetry by adding some gauge fields at the conical defects, but it doesn't quite compute the Rayleigh entropies. For the von Neumann entropies, there is no problem. I mean, these results give you non-perturbative answers for the entanglement entropy, the von Neumann entanglement entropy.
So these supersymmetric Rayleigh entropies are made such that they give the von Neumann entropy as the limit.
The limit would work. The limit would work, but they do not coincide with the trace of the nth power of the density matrix. In fact, there is another open question which is simpler. So to compute the Rayleigh entropies is a hard open question, but there is a simpler open question, which is that it's known how to preserve supersymmetry in this nth branch covering of S3 by adding some gauge fields at the conical singularities. But it's not completely clear what does that compute in flat space. So it would be nice to write a more explicit expression in terms of quantum information. What does it compute? It doesn't compute trace rho to the power n. It computes something slightly different. But it hasn't been, nobody wrote down an expression of what exactly does it compute. You can call it supersymmetric Rayleigh entropies, but it's not completely clear in what sense. Okay. So now I would like to study four-dimensional quantum filters, but actually I will start by giving an argument for the two-dimensional C theorem, which is different from the original one, but the advantage is that this particular argument can be generalized to 4 dimensions, while the original argument cannot be generalized to 4 dimensions. So I would like to go back to this fundamental inequality that is extremely important, and like to give a proof of that has a natural generalization to 4 dimensions. So the advantage is that it can be generalized while the original argument cannot be generalized. Okay, so I want to take you through some argument for how this comes about. Okay, so so the way it works is the following. So we start from some CFT in the ultraviolet, and then we trigger some RG flow to the infrared. So we start from some theory in the UV, and then we add some relevant operator, and we trigger some RG flow to some conformal filter in the infrared. So the idea is that we take this Lagrangian of the UV theory, and we add some relevant operator with some mass parameter. So let's call this guy m, let's say m to the power delta, and this would be 2, okay, so this would be 2 to the minus delta, and this would be delta. So we add a relevant operator, and this is our action. And delta is smaller than 2, so that O is relevant. Okay, so this is how you start off an RG flow. You just start from a CFT, and then you add the mass term, something with positive mass dimensions, which would trigger an RG flow. Okay, now this breaks conformal invariance. So the original theory is conformal invariant, but once you add this mass term, conformal invariance is broken. So M breaks conformal invariance. Because it's similar to the breaking of any other symmetry that you start from a theory which has a U1 symmetry, you add some parameter, you add some coupling constant that is not invariant, then the theory doesn't have the U1 symmetry anymore. And here the situation is the same. This parameter M would break conformal invariance. But one can do what's called spurious analysis. This is an idea that has been very powerful in QCD and the chiral anomalies and so on and so forth. So one can do something that you might call spurious analysis. So this is the central idea that I'm going to use. So what is spurious analysis? This is some framework which is useful in many situations. So I want to give a very simple example of what it means to use spurious analysis. So let's go back to quantum mechanics. So we have some quantum mechanics for a bunch of degrees of freedom x dot squared, and we add some potential which depends on x, but it breaks the SO. So there are, let's say, 3 x's, and so there is an SO3 symmetry. But we can add a potential which breaks the SO3 symmetry because there is an electric field. Okay, so there is some specific direction in space that you pick by some given vector E. So E is not a variable, E is given. E is a given vector. Okay, so E is a given vector. So in this theory, there is no more SO3 symmetry. While the original model has an SO3 symmetry, now there is no more SO3 symmetry. But you can still use SO3. And this kind of idea is what I refer to as spurious analysis. How do we still use SO3 even though there is no SO3 in the Hamiltonian or Lagrangian? The point is that suppose you wanted to compute the energy spectrum of this theory. So they would depend on E in some way. But we can use SO3 to constrain the dependence on E. We know that this must be a function of E squared. Only of E squared. It cannot be a function of EX, for example, by itself. It must be a function of only E squared. So EX squared plus EY squared plus EZ squared. So this kind of idea where there is some coupling constant that breaks a symmetry, but you can still constrain the dependence on this coupling constant because you can use spurious symmetry is something that I will use now very importantly. Are there any questions about this elementary thing? Okay. So we can do the same in this more abstract setting of quantum field theory where there is conformal symmetry plus a coupling constant that breaks conformal symmetry. So we can restore, at least artificially, the conformal symmetry by allowing the coupling constant to transform. So here the coupling constant is E, and we have allowed it to transform under SO3, and that leads to a non-trivial result, which is that the energy depends just on E dot E. So we can do the same with the mass parameter M. So we can write the mass parameter as E to the tau. This is just a, so first of all, instead of thinking of the coupling constant as a number, we think about it as a function. So it's a function from R2, because we're in 2 dimensions, to R. So it's a real function. So by this we mean that we promote the coupling constant to a function. That's step number 1. Step number 2 is just to rewrite this function conveniently as e to the tau. So this is just for convenience. Okay, and now under a conformal transformation, so now we can assign some pretty simple transformation rules for the function m, which, if you think about them in terms of this super artificial transformation of coupling constants, then the symmetry would seem to be restored. So it's like here that this is a function of only x dot t, of course, and x squared and e squared. So it's like here that if you assign each some transformation rule, then this thing would seem to be invariant, even though e is just a coupling constant. So under a conformal transformation, which takes the metric, so a conformal transformation is something that takes the metric to be this, with some parameter sigma. This is the general conformal transformation, or what may be more properly called the Wild transformation. So under a conformal transformation of this sort, we just need to say that tau goes to tau plus sigma. And that's it. So the original conformal field theory is invariant under this. This is the statement that the theory is conformal. Now, of course, once you introduce a mass parameter, you lose conformal invariance. But if you just accompany a conformal transformation with a transformation of the coupling constant, then the theory is invariant. This is the first non-trivial step. Is it clear of why this is true? Okay. So the simplest kind of a conformal transformation is that just rescaling of space by some factor of 2. So if you have a mass parameter, then the theory would not be invariant because the mass would need to be rescaled. So we can fix that by rescaling the mass. And that's just this statement that tau transforms to tau plus sigma. So that's the simplest version of what I'm saying. Fine. So now we suppose, so there is some RG flow from the UV to the infrared. There is some non-trivial RG flow, and the effective action in the infrared. So now let's study the infrared effective action. Would be some function of the coupling constant tau and of the fields of the infrared theory. So the fields of the infrared theory. Okay. So in the infrared, you would get just the fields of the infrared theory. There will be some conformal field theory in the infrared, and there will be some non-trivial dependence on the coupling constant. Okay, so this is the general situation that you might expect. But and now there is this is idea number 1. Now idea number 2. Idea number 2 is that there is the trace anomaly. And the system has a trace anomaly. And sorry. So the system has a trace anomaly, which in the ultraviolet is CUV, is fixed by CUV, right? This is the central charge of the ultraviolet theory. But in the infrared, the trace anomaly is fixed by C infrared, which, okay. So one has to understand, why does this not violate what's called 't Hooft anomaly matching? 'Hooft anomaly matching is the idea from like 30 years ago, or even more, that if you have a theory which has some symmetry, then the anomalies should be the same in the ultraviolet and the infrared. But let's try to test the 'Hooft anomaly matching idea for the conformal anomaly. This is an anomaly like any other anomaly, and a priori it seems that it should have worked. So, but in the UV this is CUV, and this is infrared. And if you look at simple examples, like a scalar which you deform by a mass term, then this is 0, this is non-zero. So the anomaly matching doesn't work. Why? It doesn't work because 'Hooft made an important assumption, which is that the symmetry is preserved throughout the RG flow. So 'Hooft, of course, made an important assumption. 'Hooft made the assumption that the symmetry whose anomalies you are trying to match should be a symmetry throughout the evolution of the system, not just at the endpoints. The symmetry is always present. It's present along the RG flow. Okay, so one should not a priori insist on matching the anomalies for the wild symmetry, because the wild symmetry is violated throughout the RG flow. It's present only at the conformal field at the critical point in the UV and at the critical point in the infrared. But in the middle, there is some complicated RG flow with critical exponents that are not trivial. With correlation lengths that are non-zero. And so there is no conformal symmetry, and one shouldn't try to match the anomalies. So this is why one never tries to match the anomalies for conformal symmetries, but one does match anomalies for chiral symmetries, because chiral symmetries can be preserved along RG flows, like in QCD. But here, I think, from idea number 1, you can see that you can restore the symmetry if you allow these coupling constants to transform. So in this more elaborate situation, that you also allow the coupling constants to transform, the 'Hooft anomalies must match again. This is idea number 3. So, or number 2 still. So, but now since we allow the coupling constants to transform, then the anomaly must match again. Let me explain intuitively why this is true, at least what this is similar to, that you may have seen in the past. So ordinarily, chiral anomaly matching is done for symmetries that are present throughout the RG flow, and they are not spontaneously broken. So you just match the cubic anomalies in the infrared and the cubic anomalies in the UV. And you might have seen many computations of this sort, for example, in QCD or in Seiberg duality. But one can also match anomalies for symmetries that transform non-linearly, like non-homogeneously, for symmetries that are realized non-homogeneously. For example, if the symmetry is spontaneously broken. That, for example, leads to the exact result for the pion decay to 2 photons. So there is the famous computation of the pion decay to 2 photons, and this is known to be fixed by an anomaly. So there is some anomaly coefficient in front. Why is that? Where does that come from? That comes from some anomaly matching of a chiral symmetry in QCD. So there is a certain chiral anomaly, and one can fix a coupling constant by this anomaly using the ideas of anomaly matching for symmetries that are realized non-linearly. I don't assume that you know this background from QCD, so I'll try to proceed without that. But those who know, I just wanted to emphasize that this is exactly the same, but for the conformal symmetry rather than some chiral symmetry. So are there any questions? I think before I proceed, it would be natural to take a break because this is the beginning of a longer argument. So I won't be able to do it in 5 minutes anyway.